Here, Jaymie is an astronomer from the University of British Columbia. He's a great old friend of ideacity. You've heard references to the Hubble telescope. I'm sure most of you know the Hubble is a massive enterprise involving billions of dollars. Jaymie, in true Canadian fashion, leads a project that we affectionately call the Humble. They have the Hubble. Canada has the Humble. It's a pocket project. I understood it was pulled together for what, about $4 million?
10 million.
10 now?
Canadian.
10 Canadian.
At a time when that meant something.
Yes, and stop me if I'm getting this wrong, but as I understand it, its unique quality is that it is the most stable telescope surface available, and because of this unique property, it has been able to actually come up with some exceptional discoveries. At this point, I'll ask Jaymie Matthews to pick up the story. I just noticed your shoes.
Thank you. We live in a transformative era. I'm personally convinced that 400 years from now, if there are textbooks, if there are teachers, if there are students, if there are people, that they will look back on this time, this past century, this past decade, and the decade to come, in the same way that we look at the time of Galileo 400 years ago. First, I'm going to tell you about how we're rewriting the cookbooks, the cosmic cookbook, the recipe of the universe, and how that has changed in an incredibly short period of time. Let me go back to the time of the ancient Greeks. Then, the recipe of the universe was very simple. This was their version of the periodic table. Basically 4 squares: air, water, fire, earth. And everything beyond the earth, beyond our world, the ether in the heavens. Go forward, fast forward more than 2,000 years to the time when I was an elementary school student, a high school student, even when I was a student here in Toronto studying astrophysics at U of T. And the recipe of the universe had changed, but it was still equally simple. Everything in the universe consisted of atoms and molecules of atoms and the subatomic particles, the building blocks that made those atoms and molecules. And let me not forget the photons of light, energy traveling between those atoms and molecules, emitted by them, absorbed and scattered by those atoms, molecules, and particles. That was the recipe of the universe that I started to study when I was a student, and that I was still studying when I was a student here at U of T. Before I got my Bachelor of Science degree, that had changed. The recipe of the universe changed in the late 1970s with the discovery of what eventually became known as dark matter. And the discoverer, this woman, Vera Rubin, as a graduate student, she found the evidence for this, and in the face of tremendous skepticism. You've got to admire a graduate student who sticks to her scientific principles, and as a professional astronomer, she basically bolstered the case. She found that the universe was not unfolding the way it should, or more accurately, that the galaxies in the universe were not rotating the way they should, including our own Milky Way galaxy. So here's the Milky Way. We see it from inside. It's our galactic city. As Moses mentioned, it's a city with a population of several 100 billion stars, whose city limits extend across about 120,000 light years. And if this city were Metro Toronto, we would be Etobicoke. We live in the suburb of our galactic city, out in the outskirts, away from the downtown core. And our galaxy, if you could see it from outside, would look a bit like a flying saucer or a frisbee. But if it spun like a frisbee, like a solid disk, then basically stars would be moving faster and faster the further away you were from the center of the galaxy. And that's not what our galaxy is. If all of the matter, all of the mass was concentrated where we see all of the stars and gas concentrated at the center, then the stars in our galaxy would orbit like planets in a giant solar system, obeying Kepler's third law. But that's not how they move either. This is how they move. It's like there's a whole bunch of lanes in our cosmic racetrack, and everybody's keeping pace with each other. The only way you can explain that is that if there's stuff beyond the visible galaxy, a vast spherical swarm that goes beyond the disk of our galaxy, of unseen matter that we can't detect in any other way except by its gravitational influence on the stars and gas and dust that we can see. And that applies not only to our own Milky Way galaxy, but to other galaxies. And so what you see isn't always what you get. And this was the first step in this revolution, in this revision of the cosmic recipe. In fact, Vera Rubin said at the time, in a spiral galaxy, the ratio of dark to light matter is about 10. That's probably also a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but only in about third grade. Well, we're out of third grade, but I'd say we're just entering into high school. The recipe of the universe changed again dramatically about 13 years ago. Through most of my career as an astronomer, my colleagues in cosmology have been trying to figure out whether the universe would expand forever, or whether there was enough stuff in the universe that gravity would pull it all back in, at least bringing it to a halt, or perhaps causing it to collapse from a big bang to a big crunch. Now, I don't have time to talk about the evidence for the expansion of the universe. Let me give you just one piece of evidence for the expansion of the universe in recent times. To be fair, that's probably less astronomy and more gastronomy, but let's not go into that. So this, again, was what I would be learning from the textbooks, and what cosmologists were surprised to discover 13 years ago. The expansion of the universe isn't slowing down, it's accelerating. It's getting faster and faster. There is something which is stretching apart space that works against gravity. We call that something dark energy. We could call it George. I mean, we don't know what it is. Actually, Eric Idle, some of you may know Eric from Monty Python fame. Eric has another name for it. He wrote a book called The Road to Mars, and a character in it says, what's the contracting principle of the universe? Gravity. What's the expanding force of the universe? Why, obviously, wonderfully, and marvelously, levity. Humor is the universal force that works in the opposite direction of gravity. And I wish Eric had come along with that sooner, or I would be telling you about the mystery of levity instead of dark energy. Whatever you call it, it and dark matter represent 96% of the total matter and energy, mass and energy of the universe. So if we lived in a jelly bean universe, almost all of the jelly beans would be those black licorice ones that I don't like. Here is one of the simplest pie charts you're ever going to see. 75% of the universe consists of dark energy. What is it? Got me. 21% of it exists of dark matter. What is it? We have culprits, and maybe, I think, within the next 5 to 10 years, I'll be able to answer that question, thanks to the work of my colleagues. But right now, who knows? 4% represents ordinary matter. And of that 4%, the stuff that makes up you and me and this planet, 0.03%. Everything that's part of our world is 0.03% of the entire recipe of the universe. So, in the recipe of the universe, we've gone, in less than 30 years, from being the main ingredient, the cheese in the Swiss fondue, to being one of the condiments, if you like to have ketchup with your fondue, or I prefer to think of it as one of the spices. Now that might seem depressing, going from 100% to 0.03%, but think about it. Would you like to live in a universe without spice? That would be a very, very boring, flavorless universe. It would be a bland universe. Every meal would be like an economy meal on a plane, in which if you order online, right after no preference, first option, bland. So in 3 decades, we've had a revolution in our cosmic view of the universe. And basically, 96% of the universe, we don't know what it is. Now, you might think that's not a revolution in cosmic view, that's a blindness in cosmic view. We're ignorant, and we are ignorant. But not in the sense of to misunderstand or disregard, refuse to take notice of. We're ignorant in the sense of not to know and being unaware. Our observations have shown that the universe is much more complex. There's more to it than we ever imagined. And that is a natural step in learning. Confucius wrote, "Real knowledge is to know the extent of one's ignorance." And that is part of the learning process. Let me go back to rewriting the textbooks and talking about something that you've already heard from Ray J. And I'm going to cover some of the same territory very quickly. Let me put things in perspective when talking about alien worlds. Before the 13th of March, 1781, 6 planets known to humanity. The 5 that you could see without a telescope looking up: Mercury, Venus, Mars, Jupiter, and Saturn. And the one that you could see without a telescope looking down, the Earth. After that date, the total went up to 7, with the discovery of Uranus by the British Royal Astronomer, German-born Sir William Herschel. Notice very carefully, by the way, how I pronounce the name of that planet. Uranus. We've heard all of the, they found rings around Uranus jokes. It really is pronounced Uranus. Now, let's fast forward. We won't even go into the ideas having sex part now that we're here. Let's flash forward more than 200 years. In 200 years, imagine the amazing progress. 200 years, we added 5. After the 23rd of November, 1995, the total went to 12. But this addition was a significant one. It was the watershed, the discovery of a planet around a sun-like star using the techniques that were developed right here in Canada at UBC and the University of Victoria. And as of this afternoon, 561 confirmed planets, exoplanets, around other stars, and about 1,200 candidates, of which I would estimate 90% will stand the test of time. Well, if we're going to talk about planets, we have to start at home. Our solar system, as shown here, the planets and the sun, and the dwarf planets, including poor Pluto, to scale. And the questions that astronomers ask, and the questions that anybody, you don't have to be a rocket scientist to ask this. How did the planets come to be? How did the Earth come to be? How have they changed since they were born? How does the sun influence our planet, its environment, its climate? And what is the future of our home world? And if you want to answer these questions, as a scientist, you want to study many examples. But until recently, we had only one example, our own solar system. And anybody will tell you, a sample of one is not a good way to get a balanced picture of reality. So if we really want to understand our world, we need to expand the sample to many other worlds. And that's what we've done. How do you look for exoplanets? Well, could you take a picture of an Earth around another star? That's what would seem intuitive. Well, as you've already heard, planets are faint compared to their parent stars. And a sun from afar is like staring into a lighthouse beacon head on. And somebody's left a flashlight beside that beacon, except that you can't see it because the beacon is a billion times brighter. You have to turn off that lamp to see that flashlight hidden. We can't turn off stars, probably a good thing. And so we cannot yet photograph an alien Earth. Someday, soon, but not yet. So if we're rewriting the textbooks, finding other planets, how are we doing that? If you're going to rewrite the textbooks, you need a pen. And actually, I have 4 pens. My students, my collaborators, my team have these 4 pens to rewrite the textbooks. And they're pens that draw what an astronomer would call light curves, records of the brightnesses of stars as a function of time. But these are the finest tip pens you're ever going to find for astronomy. They take ultra-precise measurements of the brightnesses of stars and the light contributed by planets orbiting around those stars. And the first of these pens, the Pioneer, Canada's first space telescope, MOST, a suitcase in space. Canadian Space Agency mission, designed, built, operated right here in Canada. And we're having babies. More ideas having sex. Bright Constellation, Bright Target Explorer, to study the several hundred brightest stars in the night sky a Canadian-Austrian-Polish collaboration using MOST technology and science. 3.5 years after we went into space, the French joined us with a mission called Corot. And looking very tiny here, only because it's in a position much further from the Earth than any of these satellites, finally the Americans joined us 7 years later with Kepler. They're exo-Earth, alien Earth hunter. And I'm a member of the Kepler Astroseismic Science Consortium. And so MOST has been joined by Corot and Kepler, and will soon be joined by Bright Constellation on this frontier. And when I was a graduate student, not far from here in London, Ontario, I couldn't have imagined that there would be 4 space missions dedicated to this kind of science, and that I'd be in charge of one of them. But that's the science fact today. So let me take you on a trip on what I call the MOST transit system. And when you see the sign there that says way out, when an astronomer like myself says way out, we mean way, way out. You've already heard about transits, the effects of a planet passing in front of its parent star. And those happen in our solar system, but only for the 2 planets that are closer to the sun than we are. Mercury, shown here in this little time-lapse picture, just skimming past the edge of the sun. And Venus. The most recent transit of Venus occurred on the 8th of June, 2004. And I was in Much Hoole, outside of Preston in central Lancashire in England, where Jeremiah Horrocks was the first person to predict and witness a transit of Venus with his own eyes from his bedroom window. And I and other scientists from around the world had gathered there to discuss the astrophysics of transits in our solar system and in other planetary systems. Now, before that, the previous transit had been in 1882. So on the 7th of June, 2004, there was not a single human being alive who had ever witnessed a transit of Venus with his or her own eyes. That night, I was in a pub in Preston and saw a charming woman and started to talk to her and invited her to join me for the evening and said, if you come with me tonight, tomorrow I will show you something that no living human being has ever seen. Turned out to be a great pickup line. Anita and I went out for 2 years, and we're still friends. Before I continue the story, I should point out that I have literally made eye contact with distant planets and galaxies. But because I'm running overtime, I am going to avoid eye contact with planet Moses. So transits are one-stop shopping for exoplanetary exploration. It's the only way we get the sizes of planets. It's the only way we get the true masses of planets directly. And these are measurements made with Canada's Space Telescope to illustrate that. So we're rewriting the textbooks. But hey, who reads books anymore? Here is a real ad. Skip real furniture. Art books look cuter than a TV table and get the job done with flair. Don't buy books to read, buy them to prop up your television set. So I'm going to rewrite the TV schedule in honor of Moses. Here's a popular show, CSI, Crime Scene Investigation. It has spawned spin-offs, CSI New York, CSI Miami, CSI Las Vegas. And I'm proposing a new show, CSI 55 Cancri E. And the pilot episode is called A Planet Where You Can't Procrastinate. Bad place for me to be. Ripped from the headlines. This isn't a tabloid like you've seen before, although some might consider the Vancouver Sun to be a tabloid, but Tiny Space Telescope reveals super-Earth. And the person who put us on the course to look for this super-Earth, a PhD student at Harvard, Becky Dawson. She told us where to drive in a virtual sense, and here's the roadmap, pointing in the direction of the constellation of Cancer to the star 55 Cancri A. And we put this star under the astronomical equivalent of a police stakeout. We monitored it nearly continuously, without interruption, for 2 weeks in February. Not only were we detectives looking for this planet, we were gamblers. We were astronomical gamblers. So what happens on Venus stays on Venus in the astronomical sense. And we were playing the slots. And in this slot machine, First, we had to figure out, did we bet on the right orbital period for this planet? Did Becky suggest the right period? Even if we did, there was only a 1 in 4 chance that the planet would pass in front of the star that we could measure. And even if it did that, there was a question of whether the planet was large enough for us to detect. Well, we did bet on the right orbital period. We did beat those odds. And yes, we hit the jackpot. And so the result of the stakeout, we cornered the culprit. And here are the data folded at the period of the planet, so you can see the dip. Very subtle dip. 1/25th of a percent. That's not the only thing that's interesting about this planet. The orbital period, if you looked at this from outside, if you were an alien, you could see it. Here's a family portrait of 2 stellar neighbors and their planets passing in front of them. When we looked at this, the period of the planet, 17 hours and 41 minutes. That's how long it takes to go around its star. That's its year. If you lived on 55 Cancri E, you wouldn't mark important dates with a calendar, you'd mark them with a clock. Hey, honey, it's 4:59, happy anniversary. I mean, literally, this is like stuff of science fiction. A year under 18 hours. Let me finish up by telling you something else that's really distinctive about this planet. And to do so, let me explain how we would understand human beings in the same way we would try to understand alien worlds. If you want to understand human beings, you need a large sample. Here's some pictures from a busy shopping intersection in Vancouver. And if there was an alien anthropologist who was studying humans, that anthropologist could collect data non-invasively on the weights and the heights of many of the humans going by, and could plot them up and find that they just don't scatter in that diagram, they're correlated. There's 2 different groups, 2 genders. There's correlations with age. It's telling you something about human beings. There are also what a statistician would call outliers, things that don't quite fit the correlation. In this case, the outliers that are at the lower right, those are very tall and not very heavy. Those are the supermodels in the distribution. And the ones in the upper left that are stout and short and heavy, those are the sumo wrestlers. Well, an Earth-based human astrophysicist can do the same thing with planets. And here is the version of that diagram for all the planets in our solar system and beyond for which we have sizes and masses. Not a very big sample yet, but much larger than we had only a few years ago. And that's where 55 Cancri E sits. It's an outlier. It's a weird planet. 8 times more massive than the Earth. Very dense, but not very big. It's a super-Earth. Basically, it's a sumo wrestler of a planet that's somehow trapped in the body of a super-Earth supermodel. And it's the poster child for new planets. Here's some of the parameters that we've discovered about this planet and their accuracies. I don't think I even know that many numbers about myself to that accuracy. And we're doing it for a planet that's orbiting a star 40 light years away. And let me finish up, now that we've given this planet a passport, to show another outlier diagram. This is a plot of how deep that transit is in parts per million, and brightness. In the bass-backwards way, we astronomers keep track of brightness with smaller numbers, meaning brighter stars on a logarithmic scale. And the star around which this planet is orbiting is 4 times brighter than the next brightest star known to have a transiting planet, and 100 times brighter than the next brightest star known to have a super-Earth, anything close to the Earth in size. And if you look in our neighborhood, there's only about 300 stars that are within 40 light years. And of those, only a couple of dozen that are like the sun. And so basically, this one, the odds are, the only transiting super-Earth that we're going to find. It's the brightest and the closest neighbor. It's the place that we're going to visit with every telescope we can to study planets. And you can see it without a telescope. You can see it by eye. You could walk out, not in Toronto because of the glare of the city lights, but you could walk out tonight and see it by eye or easily with binoculars. A beautiful sight with binoculars close to a daycare center, a maternity ward for stars, a cluster very nearby. Now, when I was a kid growing up, I was a big Star Trek fan. There was an episode of Star Trek in which Captain Kirk went back to the Earth in the 1930s and was hitting up a young Joan Collins. And he points up and says, "See that star? There's a planet around that star that basically the most romantic poet in the universe lives." That's reality now. I can go outside and with a student and say, "See that star? There's a super exotic super-Earth that's orbiting around it every 18 hours. I can tell you what that world is like." And that represents a completely new era and something almost as exciting as making eye contact with planet Moses.
Give us a picture, give us a picture. That's great, Jaymie. Now that's enthusiasm, that's enthusiasm.
I just have to point out, because I'm going to be followed by a quickie, and I tend to last a lot longer than expected.
Hey, Jaymie, here's an interesting tidbit. I don't know if you know this. It's new to me. But the United Nations is set to create an Office of Outer Space Affairs. Did you know that?
I've had many outer space affairs myself.
Apparently, a Miss Maslin Othman, who's a Malaysian astrophysicist, is going to take on the task of coordinating human response if and when extraterrestrials make contact. There you go.